In thermodynamics, the Helmholtz free energy is a thermodynamic potential that measures the useful work obtainable from a closed thermodynamic system at a constant temperature and volume. The negative of the change in the Helmholtz energy during a process is equal to the maximum amount of work that the system can perform in a thermodynamic process in which volume is held constant. If the volume were not held constant, part of this work would be performed as boundary work. This makes the Helmholtz energy useful for systems held at constant volume. Furthermore, at constant temperature, the Helmholtz energy is minimized at equilibrium. In contrast, the Gibbs free energy or free enthalpy is most commonly used as a measure of thermodynamic potential, especially in chemistry, when it is inconvenient for applications that do not occur at constant pressure. For example, in explosives research, Helmholtz free energy is often used, since explosive reactions by their nature induce pressure changes. It is also frequently used to define fundamental equations of state of pure substances. The concept of free energy was developed by Hermann von Helmholtz, a German physician and physicist, and first presented in 1882 in a lecture called, "On the Thermodynamics of Chemical Processes." From the German word Arbeit work, the International Union of Pure and Applied Chemistry (IUPAC) recommends the symbol A and the name Helmholtz energy. In physics, the symbol F is also used in reference to free energy or Helmholtz function. Definition. The Helmholtz energy is defined as a U minus T S display style A equiv UTS, where A is the Helmholtz free energy SI joules CGS ergs, U is the internal energy of the system SI joules CGS ergs, T is the absolute temperature kelvins of the surroundings modeled as a heat bath, S is the entropy of the system SI, joules per Kelvin, CGS, ergs per Kelvin. The Helmholtz energy is the Legendre transformation of the internal energy U, in which temperature replaces entropy as the independent variable. Formal development. The first law of thermodynamics in a closed system provides d U equals delta Q plus delta W. Display style mathrm d U equals delta Q plus delta W, where U display style U is the internal energy, delta Q display style delta Q is the energy added as heat, and delta W display style delta W is the work done on the system. The second law of thermodynamics for a reversible process yields delta Q equals T d S display style delta Q equals T mathrm d S. In case of a reversible change, the work done can be expressed as delta W equals minus P d V. Display style delta W equals P mathrm d V. Ignoring electrical and other non-PV work, d U equals T d S minus P d V. Display style mathrm d U equals T mathrm d S P mathrm d V. Applying the product rule for differentiation to d Ts equals TdS plus SdT, it follows d U equals d T S minus S d T minus P d V. Display style mathrm d U equals mathrm d T S S mathrm d T P mathrm d V, and d U minus T S equals minus S D T minus P D V. Display style mathrm d uts equals s mathrm d tp mathrm d v. The definition of A equals U minus ts enables to rewrite this as d A equals minus s d t minus p d v. Display style mathrm d A equals s mathrm d t p mathrm d v. Because A is a thermodynamic function of state, this relation is also valid for a process without electrical work or composition change that is not reversible, as long as the system pressure and temperature are uniform. Minimum free energy and maximum work principles. The laws of thermodynamics are most easily applicable to systems undergoing reversible processes or processes that begin and end in thermal equilibrium, although irreversible quasi-static processes or spontaneous processes in systems with uniform temperature and pressure (UPT processes) can also be analyzed based on the fundamental thermodynamic relation as shown further below. First, if we wish to describe phenomena like chemical reactions, it may be convenient to consider suitably chosen initial and final states in which the system is in metastable thermal equilibrium. If the system is kept at fixed volume and is in contact with a heat bath at some constant temperature, then we can reason as follows. Since the thermodynamical variables of the system are well defined in the initial state and the final state, the internal energy increase delta U display style delta U, the entropy increase delta S display style delta S, and the total amount of work that can be extracted performed by the system W display style W are well defined quantities. Conservation of energy implies delta U bath plus delta U plus W equals 0. Display style delta U underscore text bath plus delta U plus W equals 0. The volume of the system is kept constant. This means that the volume of the heat bath does not change either, and we can conclude that the heat bath does not perform any work. This implies that the amount of heat that flows into the heat bath is given by Q bath equals delta U bath equals minus delta U plus W. Display style Q underscore text bath equals delta U underscore text bath equals delta U plus W. The heat bath remains in thermal equilibrium at temperature T no matter what the system does. Therefore, the entropy change of the heat bath is delta S bath equals Q bath T equals minus delta U plus W T. Display style delta S underscore text bath equals frac Q underscore text bath T equals frac delta U plus W T. The total entropy change is thus given by delta S bath plus delta S equals minus delta U minus T delta S plus W T. Display style delta S underscore text bath plus delta S equals frac delta U T delta S plus W T. Since the system is in thermal equilibrium with the heat bath in the initial and the final states, T is also the temperature of the system in these states. The fact that the system's temperature does not change allows us to express the numerator as the free energy change of the system. Delta S bath plus delta S equals minus delta A plus W T. Display style delta S underscore text bath plus delta S equals frac delta A plus W T. Since the total change in entropy must always be larger or equal to 0, we obtain the inequality W minus delta A display style W leq delta A. We see that the total amount of work that can be extracted in an isothermal process is limited by the free energy decrease, and that increasing the free energy in a reversible process requires work to be done on the system. If no work is extracted from the system, then delta A 0 display style delta A leq 0. And thus for a system kept at constant temperature and volume and not capable of performing electrical or other non-PV work, the total free energy during a spontaneous change can only decrease. This result seems to contradict the equation DA minus S dt minus P dV, as keeping T and V constant seems to imply DA 0, and hence A constant. In reality there is no contradiction, in a simple one-component system, to which the validity of the equation DA minus S dt minus P dV is restricted. No process can occur at constant T and V, since there is a unique P T, V relation, and thus T, V, and P are all fixed. To allow for spontaneous processes at constant T and V, one needs to enlarge the thermodynamical state space of the system. In case of a chemical reaction, one must allow for changes in the numbers Nj of particles of each type J. The differential of the free energy then generalizes to d A equals minus S d T minus P d V plus J mu J d N J. Display style DA equals S DTP dV plus sum underscore J mu underscore J dN underscore J, where the N J display style N underscore J are the numbers of particles of type J, and the mu J display style mu underscore J are the corresponding chemical potentials. This equation is then again valid for both reversible and non-reversible UPT changes. In case of a spontaneous change at constant T and V without electrical work, the last term will thus be negative. In case there are other external parameters, the above relation further generalizes to d A equals minus S d T minus I x I d x I plus J mu J d N J. Display style DA equals S dt sum underscore I x underscore I dx underscore I plus sum underscore J mu underscore J dN underscore J. Here the x I display style x underscore I are the external variables, and the x I display style x underscore I the corresponding generalized forces. Topic: Relation to the canonical partition function. A system kept at constant volume, temperature, and particle number is described by the canonical ensemble. The probability to find the system in some energy eigenstate R is given by P R equals E minus beta E R Z. Display style P underscore R equals frac E caret beta E underscore R Z, where beta 1 K T display style beta equiv frac 1 kt E R equals energy of eigenstate R display style E underscore R equals text energy of eigenstate R Z equals R E minus beta E R display style Z equals sum underscore R E caret beta E underscore R. Z is called the partition function of the system. The fact that the system does not have a unique energy means that the various thermodynamical quantities must be defined as expectation values. In the thermodynamical limit of infinite system size, the relative fluctuations in these averages will go to zero. The average internal energy of the system is the expectation value of the energy and can be expressed in terms of Z as follows: U E equals R P R E R equals minus log Z beta. Display style U equiv Langle E wrangle equals sum underscore R P underscore R E underscore R equals frac partial log Z partial beta. If the system is in state R, then the generalized force corresponding to an external variable x is given by x R equals minus E R x. Display style x underscore R equals frac partial E underscore R partial x. The thermal average of this can be written as x equals R P R x R equals 1 beta log Z x. Display style x equals sum underscore R P underscore R x underscore R equals frac 1 beta frac partial log Z partial x. Suppose that the system has one external variable x display style x. Then changing the system's temperature parameter by d beta display style d beta and the external variable by d x display style dx will lead to a change in log z display style log z d log z equals log z beta d beta plus log z x d x equals minus u d beta plus beta x d x. Display style d log z equals frac partial log z partial beta d beta plus frac partial log z partial x dx equals u d beta plus beta the 10th dx. If we write u d beta display style u d beta as u d beta equals d beta u minus beta d u display style u d beta equals d beta u beta do, we get d log z equals minus d beta u plus beta d u plus beta x d x display style d log z equals d beta u plus beta do plus beta the 10th dx. This means that the change in the internal energy is given by d u equals 1 beta d log z plus beta u minus x d x display style do equals frac 1 beta d log z plus beta u x dx. In the thermodynamic limit, the fundamental thermodynamic relation should hold d u equals T d s minus x d x display style do equals T dsx dx. This then implies that the entropy of the system is given by S equals K log Z plus U T plus C. Display style S equals K log Z plus frac U T plus C, where C is some constant. The value of C can be determined by considering the limit T0. In this limit, the entropy becomes S equals K log omega 0. Display style S equals K log omega underscore 0, where omega 0 display style omega underscore 0 is the ground state degeneracy. The partition function in this limit is omega 0 e minus beta u 0 display style omega underscore 0 e caret beta u underscore 0, where u 0 display style u underscore 0 is the ground state energy. Thus, we see that C equals 0 display style C equals 0, and that A equals minus K T log Z display style A equals KT log Z. Topic: Relating free energy to other variables. Combining the definition of Helmholtz free energy A equals U minus T S display style A equals UTS, along with the fundamental thermodynamic relation D A equals minus S D T minus P D V plus mu D N display style da equals S DTP dV plus mu dN. One can find expressions for entropy, pressure and chemical potential. S equals minus a T V N P equals minus a V T N mu equals a N T V display style S equals big frac partial T big underscore V N quad P equals big frac partial V big underscore T N quad mu equals big frac partial N big underscore T V. These three equations, along with the free energy in terms of the partition function A equals minus k t log z display style a equals kt log z allow an efficient way of calculating thermodynamic variables of interest given the partition function and are often used in density of state calculations. One can also do Legendre transformations for different systems. For example, for a system with a magnetic field or potential, it is true that m equals minus a b t n v equals a q n t. Display style m equals big frac partial b big underscore t n quad v equals big frac partial q big underscore n t. Topic: Bogoliubov inequality. Computing the free energy is an intractable problem for all but the simplest models in statistical physics. A powerful approximation method is mean field theory, which is a variational method based on the Bogoliubov inequality. This inequality can be formulated as follows. Suppose we replace the real Hamiltonian h h of the model by a trial Hamiltonian h tilde h, which has different interactions and may depend on extra parameters that are not present in the original model. If we choose this trial Hamiltonian such that h tilde equals h display style left Langle tilde h right wrangle equals Langle h wrangle, where both averages are taken with respect to the canonical distribution defined by the trial Hamiltonian h tilde display style tilde h, then a tilde display style a leq tilde a, where a display style a is the free energy of the original Hamiltonian and a tilde display style tilde a is the free energy of the trial Hamiltonian. By including a large number of parameters in the trial Hamiltonian and minimizing the free energy, we can expect to get a close approximation to the exact free energy. The Bogoliubov inequality is often formulated in a slightly different but equivalent way. If we write the Hamiltonian as h equals h 0 plus delta h display style h equals h underscore 0 plus delta h, where h 0 display style h underscore 0 is exactly solvable, then we can apply the above inequality by defining h tilde equals h 0 plus delta h 0 display style tilde h equals h underscore 0 plus Langle delta h wrangle underscore 0. Here we have defined x 0 display style Langle x wrangle underscore 0 to be the average of x over the canonical ensemble defined by h 0 display style h underscore 0. Since h tilde display style tilde h defined this way differs from h 0 display style h underscore 0 by a constant, we have in general x 0 equals x display style Langle x wrangle underscore 0 equals Langle x wrangle. Therefore h tilde equals h 0 plus delta h equals h Display style left Langle tilde h right Rangle equals big Langle h underscore 0 plus Langle delta h Rangle big Rangle equals Langle h Rangle, and thus the inequality a tilde display style a leq tilde a holds. The free energy a tilde display style tilde a is the free energy of the model defined by h 0 display style h underscore 0 plus delta h display style Langle delta h Rangle. This means that a tilde equals h 0 0 minus t s 0 plus delta h 0 equals h 0 minus t s 0 display style tilde a equals Langle h underscore 0 Rangle underscore 0 ts underscore 0 plus Langle delta h Rangle underscore 0 equals Langle h Rangle underscore 0 ts underscore 0, and thus a h 0 minus t s 0 display style a leq Langle h Rangle underscore 0 ts underscore 0. Topic: Proof. For a classical model, we can prove the Bogoliubov inequality as follows. We denote the canonical probability distributions for the Hamiltonian and the trial Hamiltonian by p r display style p underscore r and p tilde r display style tilde p underscore r respectively. From Gibbs's inequality we know that r p tilde r log p tilde r r p tilde r log p r display style sum underscore r tilde p underscore r log left tilde p underscore r right geq sum underscore r tilde p underscore r log left p underscore r right holds. To see this, consider the difference between the left-hand side and the right-hand side. We can write this as r p tilde r log p tilde r p r display style sum underscore r tilde p underscore r log left frac tilde p underscore r p underscore r right. Since log x 1 minus 1 x display style log left x right geq1 frac 1 x, it follows that r p tilde r log p tilde r p r r p tilde r minus p r equals 0. Display style sum underscore r tilde p underscore r log left frac tilde p underscore r p underscore r right geq sum underscore r left tilde p underscore r p underscore r right equals 0. Where in the last step we have used that both probability distributions are normalized to 1. We can write the inequality as log p tilde r log p r display style left langle log left tilde p underscore r right wrangle geq left langle log left p underscore r right wrangle, where the averages are taken with respect to p tilde r display style tilde p underscore r. If we now substitute in here the expressions for the probability distributions, p r equals exp minus beta h r z display style p underscore r equals frac exp left beta h left r right z and p tilde r equals exp minus beta h tilde r z tilde display style tilde p underscore r equals frac exp left beta tilde h left r right rig ht tilde z, we get minus beta h tilde minus log z tilde minus beta h minus log z display style left langle beta tilde h log left tilde z right wrangle geq left langle beta h log left z right wrangle. Since the averages of h display style h and h tilde display style tilde h are by assumption identical, we have a tilde display style a leq tilde a. Here we have used that the partition functions are constants with respect to taking averages and that the free energy is proportional to minus the logarithm of the partition function. We can easily generalize this proof to the case of quantum mechanical models. We denote the eigenstates of h tilde display style tilde h by r display style left r right wrangle. We denote the diagonal components of the density matrices for the canonical distributions for h display style h and h tilde display style tilde h. In this basis is p r equals r exp minus beta h z r display style p underscore r equals left langle r left frac exp left beta h right z right r right wrangle and p tilde r equals r exp minus beta h tilde z tilde r equals exp minus beta e tilde r z tilde display style tilde p underscore r equals left langle r left frac exp left beta tilde h right tilde z right r right wrangle equals frac exp left beta tilde e underscore r right tilde z, where the e tilde r display style tilde e underscore r are the eigenvalues of h tilde display style tilde h. We assume again that the averages of h and h tilde display style tilde h in the canonical ensemble defined by h tilde display style tilde h are the same. H tilde equals h display style left langle tilde h right wrangle equals left langle h right wrangle, where h equals R P tilde R R H R display style left Langle H right rangle equals sum underscore R tilde P underscore R left Langle R left H right R right rangle. The inequality R P tilde R log P tilde R R P tilde R log P R display style sum underscore R tilde P underscore R log left tilde P underscore R right GEQ sum underscore R tilde P underscore R log left P underscore R right still holds as both the P R display style P underscore R and the P tilde R display style tilde P underscore R sum to 1. On the L H S we can replace log P tilde R equals minus beta E tilde R minus log Z tilde display style log left tilde P underscore R right equals beta tilde E underscore R log left tilde Z right. On the right hand side we can use the inequality exp x R exp x R display style left Langle exp left x right right rangle underscore R geq exp left left Langle x right rangle underscore R right, where we have introduced the notation y R R y R display style left Langle y right rangle underscore R equiv left Langle R left y right R right rangle for the expectation value of the operator y in the state R. See here for a proof. Taking the logarithm of this inequality gives log exp x R x R display style log left Langle exp left x right right rangle underscore R right geq left Langle x right rangle underscore R. This allows us to write log P R equals log exp minus beta H minus log Z R minus beta H minus log Z R display style log left P underscore R right equals log left Langle exp left beta H log left Z right right rangle underscore R right geq left Langle beta H log left Z right rangle underscore R. The fact that the averages of H and H tilde display style tilde H are the same then leads to the same conclusion as in the classical case. A tilde display style a leq tilde a. Topic: Generalized Helmholtz energy. In the more general case, the mechanical term pdv must be replaced by the product of volume, stress, and an infinitesimal strain d a equals v I j sigma I j d epsilon I j minus s d t plus I mu I d n I Display style mathrm d a equals v sum underscore ij sigma underscore ij mathrm d var epsilon underscore ij s mathrm d t plus sum underscore I mu underscore I mathrm d n underscore I, where sigma I j display style sigma underscore ij is the stress tensor and epsilon I j display style var epsilon underscore ij is the strain tensor. In the case of linear elastic materials that obey Hooke's law, the stress is related to the strain by sigma I j equals c I j k l epsilon k l. Display style sigma underscore ij equals c underscore ijkl var epsilon underscore kl, where we are now using Einstein notation for the tensors, in which repeated indices in a product are summed. We may integrate the expression for d a display style mathrm d a to obtain the Helmholtz energy a equals 1 2 v c I j k l epsilon I j epsilon k l minus s t plus I mu I n I equals 1 2 v sigma I j epsilon I j minus s t plus I mu I ni display style begin aligned and equals frac 1 2 vc underscore ijkl var epsilon underscore ij var epsilon underscore kl street plus sum underscore I mu underscore I n underscore I and equals frac 1 2 v sigma underscore ij var epsilon underscore ij street plus sum underscore I mu underscore I n underscore I. End aligned. Application to fundamental equations of state. The Helmholtz free energy function for a pure substance together with its partial derivatives can be used to determine all other thermodynamic properties for the substance. See, for example, the equations of state for water, as given by the IAPWS in their IAPWS 95 release. Application to training autoencoders. Hinton and Zellum derive an objective function for training autoencoders based on the minimum description length (MDL) principle. The description length of an input vector using a particular code is the sum of the code cost and reconstruction cost. They define this to be the energy of the code, for reasons that will become clear later. Given an input vector, they define the energy of a code to be the sum of the code cost and the reconstruction cost. The true expected combined cost is F equals I P I E I minus H display style F equals sum underscore I P underscore I E underscore I H, which has exactly the form of Helmholtz free energy. See also Gibbs free energy and thermodynamic free energy for thermodynamics history overview and discussion of free energy. Grant potential, enthalpy, statistical mechanics. This page details the Helmholtz energy from the point of view of thermal and statistical physics. Bennett acceptance ratio for an efficient way to calculate free energy differences and comparison with other methods.